Imagine walking toward a wall. First, you cover exactly half the total distance. Then you step forward to cover half of the remaining distance, then half of that. If you keep moving in this pattern, you are always leaving a tiny fraction of space between you and the wall. Logically, you never actually complete the journey. Looking at this sequence of fractions, we can translate that physical walk into mathematics. With every step, the missing piece of the journey shrinks toward zero. Even though the addition process is infinite, the total distance covered gets as close to 1 as we wish. This establishes a very specific mathematical rule. A limit tells us the exact value that a changing quantity is approaching, proving that we can calculate a clear destination even if a process never formally arrives there. This table and graph show the function y equals 1 divided by x. As we plug in larger and larger values for x, from 10 to 100 to 1,000, the resulting fraction becomes positive and very small. As we extend the graph to the right, we can see this long-run behavior visually. The curve flattens out, approaching a horizontal line exactly at 0. The statement here is that as x grows to infinity, the limit is 0. Infinity describes a direction of unbounded growth, not an ordinary real number we can plug in. By using a limit, we guarantee the ultimate long-run behavior of the equation without having to calculate larger numbers forever. Let's look at this complex rational function. To understand its trajectory, we rewrite the algebra to separate out the fractional piece. As x grows without bound, that fraction shrinks completely to 0, leaving a horizontal asymptote of 2. But notice what happens near x equals 10, where the original denominator becomes 0. The behavior splits. Approaching 10 from the left, the values decrease rapidly toward negative infinity. Approaching from the right, they increase without bound toward positive infinity. Because the left and right trajectories completely disagree at this breaking point, there is no single two-sided finite limit here. A limit requires a consistent, verifiable pattern of approach. There is a common misconception taught in early algebra that an asymptote is an impenetrable physical barrier, a wall that a graph is forbidden to cross. This graph shows the function 2 plus the sine of x, all divided by x. Because the sine wave naturally fluctuates up and down, the line repeatedly pierces right through its horizontal asymptote. But as x continues to grow, those waves dampen, and the graph hugs the line tighter and tighter. The asymptote is merely a mathematical guide for the final destination. It describes the long-run behavior, entirely ignoring the localized bumps along the journey. Here is a curving parabola. If we want to find the exact slope of the curve frozen at a single point, we hit a wall. Calculating a slope requires 2 points, but we only have 1. We solve this by plotting a second point slightly further up the curve, stepping forward by a tiny non-zero amount we call delta x. Connecting them creates a secant line. As we force that delta x gap to shrink closer and closer to 0, the second point slides down the curve. The secant line settles into position, approaching the exact angle of our target tangent line. Looking at the algebraic formula for this slope, we see the critical problem. We cannot simply set our step width to 0 from the very beginning, because the original difference quotient contains division by 0. Instead, we simplify the expression while delta x is still a real non-zero number. Only after the terms cancel out do we apply the limit, watching as the remaining piece shrinks toward 0, revealing a final, instantaneous slope of 14. Calculus functions because limits allow us to analyze a moving target right up to the absolute edge of 0 without breaking the laws of mathematics to get there. This visual evidence, from the physical steps toward a wall, to the unbounded growth of a fraction, to the vertical split of a rational function, and the sliding slope of a tangent line, all rely on the exact same logic. Limits give mathematics a precise language for describing approach. They are the mechanism that connects endless, dynamic processes to static, solvable truths.